Hi everyone, welcome to Home Learning Lab. In this video, we are going to solve this problem from 2019 JEE Advanced paper 1. This is the second problem in the paper from mathematics section. It says so they are defining a matrix. M is a 2 by 2 matrix which has some trigonometric functions inside, and this matrix has been decomposed. So it's alpha times the identity matrix, beta times the matrix inverse, and they are defining alpha. Both alpha and beta are basically functions of theta, and we are supposed to find alpha star plus beta star, where alpha star is the minimum of this set. Like, if alpha is a function of theta, find the minimum value that function takes. Similarly, if beta is a function of theta, find the minimum value that function takes and give me the sum of those values. That's basically what they have given in the question. A matrix which has been decomposed into this form that they have mentioned here, and we need to find out alpha and beta, like how they are functions of theta in what fashion, and for those functions you need to find the minimum values. Some of those minimum values is the answer. Now, the moment I look at this particular form, right, so we have a matrix and it has been decomposed into identity matrix and some other form, matrix inverse. One particular property needs to strike my mind. So what comes to my mind is, this is kind of similar to the polynomial, the characteristic equation of matrices, and I can use CH theorem, the Cayley-Hamilton theorem in this scenario. But more on this latter, this problem can be solved from scratch as well. So if someone doesn't know CH theorem, then also this problem can be solved. So I'll just go over that approach first and then come back to the approach that involves CH theorem, which is there is some issue with pen. So let's go over the standard approach first. So let me just write this here. So this would be the first approach. This is the normal approach. So for the normal approach, I would recommend people to just take sine square theta as t, because that would reduce the number of letters that you have to write. So in an exam scenario, you can't keep on writing sine, cos, sine, cos. So just assume sine square theta as t just for sake of convenience. Then your matrix would look like M is t square minus 1 plus sine square theta. So minus 1 plus t. This is 1 plus cos square theta. Cos square theta is 1 minus sin square theta. So it's 2 minus sin square theta, or 2 minus t. And cos to the power 4 theta is cos square theta whole square, or 1 minus sin square theta. This will be 1 minus. Yeah, this will be 1 minus t. 1 minus sin square theta is cos square theta. It's whole square. So from here, what you can do is you can literally actually just equate it with what has been given, which is alpha times identity matrix 1 0 0 1 plus beta times matrix inverse. So we know that if we have a matrix 2 by 2 matrix A, B, C, again, let me just write it the correct way. Apologies for that. Let's say I have a 2 by 2 matrix which looks like this. A matrix inverse is basically adjoint A by mod A. So let's say A was this, then adjoint of A for a 2 by 2 matrix would be it would be D, A minus B and minus C. So we flip these elements on the main diagonal and we multiply the elements on the other diagonal by minus 1. And you can actually apply the standard rules to calculate the adjoint of a matrix and convince yourself that indeed for a 2 by 2 matrix which has elements like A, B, C, D, the adjoint would look like this. So adjoint A and determinant of A is also fairly simple to calculate. Since it's a 2 by 2 matrix, it's just AD minus BC. And once you have this, all you need to do is you just substitute all these values here, right? So you have M, you can just do the same thing for M. So do this particular math that has been mentioned here. divide it with determinant, and then all you have to do is you can solve for alpha and beta. So alpha will be some function of t, f of t, and beta will also be some function of t. Let's call it g of t. But of course, t is sine square theta, so you get the trigonometric functions. And for both of these functions, you can just differentiate and find where these are minimum, or you can form whole squares of those and then see where you can get the minimum values for those functions, and you will arrive at your answer. So that would be the first approach. Like, let's say you do not know what Cayley-Hamilton theorem is, then also it's not an excuse to not solve this problem. So you can just solve this problem in the standard approach as well. The only thing is that if you keep on writing sin square theta, cos square theta repeatedly in exam, you might goof up. So just do a replacement of variables and then just follow the standard process. There will be a bit of legwork involved. So by legwork, I mean that you will have to keep on writing a lot of things repeatedly, and you'll have to make sure that everything is perfect. You do not goof up in signs or terms or coefficients, and you will get to the answer. So once you get functions, the process is fairly standard. For those functions, you just need to find where they achieve minimum. You can differentiate and find that, but if you differentiate, then also the question arises whether it's a maxima or a minima. So it's always a good idea to try to convert them into perfect squares, and then it's very easy to see where the function will at its minimum. Having said that, this would be the standard approach, not the advanced approach to solve this problem. The advanced approach, like I mentioned in the start of the video, would involve using CH theorem, the Cayley-Hamilton theorem. So what Cayley-Hamilton theorem basically states is that, let's say you have a matrix A. I would again go back to, let me use gray color actually. So let's say you have a matrix A, which is n by n matrix. If you have n by n matrix called A, then the characteristic equation for this matrix A, the polynomial equation, would be determinant of I, which is identity matrix, n by n identity matrix, multiplied with x minus A. This would be the characteristic polynomial. And what Cayley-Hamilton theorem states is that this characteristic polynomial equation that you get, this will be equal to 0. That's what it states. So in matrix form, what effectively Cayley-Hamilton theorem states is that if you have a matrix A, then if you apply all the determinant forms, so for polynomial, we can actually check how this will look like. So I times x would basically be x 0 0 x, and if let's say A was some matrix A, B, C and D, then we are subtracting this from it, A, B, C, D. This is just for completeness purpose. So I am looking at this new matrix, x minus A, minus B, minus C and x minus D, and I want to compute determinant for this matrix. So this will be this product, subtract BC from it. So determinant is x minus A times x minus D, minus C into minus B is just positive, so it's BC. And if you expand this, you will get x square minus A plus D times x plus AD minus BC. So in matrix form, so this is the polynomial form, and if I convert it into matrix form, what I'll get is A square. So for a matrix A, it will be A square minus A plus D. Please note that A plus D are some of the elements of the main diagonal, which is trace of a matrix. So it's trace of A times A plus AD minus BC. AD minus BC is determinant of A plus determinant of A times I, n by n identity matrix. Since this is an n by n matrix, this is an n by n matrix, and we're adding something to it. So determinant is a scalar value, so we have to multiply it with an n by n matrix to keep everything in form of n by n matrices. This will be a 0 matrix of n by n form. So this will be a 0 matrix which has dimension n by n. That's basically what the statement of Cayley-Hamilton theorem is, that for any matrix, if you write up its characteristic polynomial equation, it will be equal to 0, and that can be generalized to matrix form. So that particular equation will be basically a 0 matrix. In case of scalar determinants, it will be literally just 0. In case of matrices, it will be a matrix filled with zeros, as simple as that. Now, keeping this primer in mind for from Kelly-Hamilton theorem, for this particular matrix M also we can apply the same thing. So for the given matrix M, I would have M square minus trace of M times M plus determinant of M times identity matrix. This will be a 2 by 2 identity matrix, because in the problem we have a 2 by 2 matrix. M is a 2 by 2 matrix. This will be a 0 matrix, right? Okay, so this is a 0 matrix, 2 by 2 0 matrix. This is what we have. This is what we know. But as per the question, they have given that if you check the original statement in the problem, they are saying that M is alpha times identity matrix plus beta times M inverse. So M is alpha times identity matrix plus beta times M inverse. Of course, what I will now do is I will try to compare these two equations. In order to compare, I will multiply this particular equation with M matrix on both sides to get M square is alpha times identity matrix into M plus beta times M inverse into M is just identity matrix. So it's just beta that I am left with, beta times identity matrix. Now, if I compare both these sides, so from the first equation, actually I can write M square is trace of M times M minus determinant of M times identity matrix. Remember, on RHS we just have a 0 matrix, so it doesn't matter. And if we compare these two sides, this is same as this. So alpha times identity matrix is just trace of M. This is the first thing that I know. And what's more is, for this particular part, if you compare this, beta is literally negative of determinant of M. So the second part is beta is negative of determinant of M. Right. So I have actually used CH theorem in this particular problem to arrive at the forms of alpha and beta, so to speak. Now, of course, we can do something more about this. I mean, if at all you are interested in exactly finding out how this would look like, how to exactly find out alpha, how that would come out to be. So remember that if you are saying that trace of a matrix is something here which is being multiplied, everything is in a matrix form itself. So here, effectively, if you multiply this with identity matrix inverse on both sides, it will cancel out. So it's same as saying alpha is same as trace of M. And we have already found out a direct form for beta. So from the given question, we have, if I write out the matrix, M is sine to the power 4 theta cos this form. So I'll just replicate M here once again. So M was sine to the power 4 theta minus 1 minus sine square theta. This is 1 plus cos square theta and cos to the power 4 theta. Yeah. So just a quick move back to what I said a couple minutes ago, because it might be confusing to people, is that in this matrix form equation for Kelly-Hamilton theorem, everything is in matrix form. So when I write trace of a matrix also, it is in a matrix form. So here when I get alpha times I is same as the trace of a matrix, if you multiply I inverse on both sides, ultimately you will have the trace matrix on one side and alpha on the other. So you can literally just say that alpha is same as the trace value of the matrix. Having said that, we can actually now find out both those functions, alpha and beta. So here alpha would be trace of the matrix, which is sine to the power 4 theta plus cos to the power 4 theta. And I'm supposed to find the minimum value for this function. Instead of doing differentiation and moving into calculus and all of that, I can just form whole squares. So it's very easy to form whole square here. Sin square theta plus cos square theta, it's whole square. it will be this part plus 2 sine square theta cos square theta, just subtract it, 2 sine square theta cos square theta. This is 1 minus, let's take sine 2 theta ka whole square. This will be 4 sine square theta cos square theta divided upon 2. Now, this is the function alpha. So alpha of theta that they are asking is this function. You want to minimize this. In order to minimize something, this negative part has to be maximized. In other words, sine 2 theta has to be maximized. Sine 2 theta maximum value is 1. So just plug in 1 here. So alpha star is 1 minus 1 upon 2, which is half. This is the first part that we get. I'll go back over what I said. In order to minimize this function, this negative part has to be as high as possible. And sine 2 theta is the only functional element here. It has to be as high as possible and its highest value is 1. When 2 theta will be what? Pi by 2 or theta is pi by 4. Hence, the minimum value possible or alpha star is 1 minus 1 by 2, which is half. That is the first part of the problem we are done with. Coming to the second part of the problem, beta is negative of determinant of m. So beta is negative of, if I compute determinant of m, that is sine to the power 4 theta cos to the power 4 theta minus this product. If I take this minus common, it will become plus, and it will give me 1 plus sine square theta multiplied with 1 plus cos square theta. Now, this actually looks a bit difficult to untangle, but one observation will help us to solve this. This is basically what? If you think about it, this is sine square theta cos square theta whole square. So, can I do something with sine square theta and cos square theta? I mean, okay. Yeah. So if we detangle this, this will be 1 plus, 1 plus sine square theta plus cos square theta, sine square theta plus cos square theta plus the product sine square theta into cos square theta. Now this sine square theta plus cos square theta is what? So it's effectively 2 plus this sine square theta cos square theta, and we have this term sine to the power 4 theta cos to the power 4 theta. Alright, just for completeness, let me write that here also. Okay. So this is the final form. We have to somehow find the minima of this function. And of course, again, not going to differential calculus and all, we should try to create whole squares out of it, try to reform it, rearrange it so that we can form whole squares out of it. What we can just do here is, this thing is sine 2 theta. If I write 2 sine square theta, 2 sine theta cos theta, if I raise this to the power 4, it will be what? Sine to the power 4 theta cos to the power 4 theta, but it will have a power of 16, so just divide it by 16, plus keep this 2 as it is, plus again do the same thing, sine 2 theta. If we take the whole square, it will be 4 times of, so 2 sine theta cos theta ka whole square is 4 times, so we divided with 4. And this is all that we need to do. You don't have to do a whole squaring or anything, because you have beta as a function of theta now. You just have sine 2 theta to deal with. So if you have multiple terms, initially you have multiple terms, right? You have sine and cos multiplied with each other. That complicates our life. Here you just have the function defined in terms of sine 2 theta. And you need minimum of this function. Negative is outside. So to minimize this function, whatever is inside should be as high as possible. And since the only variable is sine 2 theta, we need to maximize sine 2 theta. In other words, it's actually the same thing that we did for alpha of theta as well. So here negative is outside. You need to minimize the overall thing, or in other words, maximize what is inside. Since everything is in terms of sine 2 theta, just maximize sine 2 theta, or sine 2, or in other words, sine 2 theta should become 1. 2 theta is pi by 2, theta is pi by 4, the same thing. So the minimum value beta star will come out to be, you just plug sine 2 theta as 1 in this equation, it will be 1 by 16 plus 2 plus 1 by 4. You need to normalize it. This is negative of, I don't know, so 2, 16, 32, 33, then plus 37 upon 16. This is my beta star. So this is beta star and this is alpha star. So alpha star plus beta star is minus 37 plus 8 upon 16 or minus 29 by 16. This is an answer for this given problem, which is option number C. I would definitely say it's not that easy to solve in an exam scenario. So there are two approaches. In the first approach, you just assume sin squared theta as t to simplify your calculations, and then just move ahead with the problem. Can compute the inverse of the matrix adjoined by a determinant, and just go ahead, compare the terms, get the two functions, and then try to find the minimum values. Or we can do a smart utilization of the CH theorem, which basically states that in matrix form for any matrix, this will be the characteristic equation, right? And then for the given matrix, we have some equation given. We'll try to convert it into the same characteristic equation. We'll try to compare the coefficients. We'll try to compare the two equations, compare the coefficients of the terms of the two equations to arrive at the fact that alpha is trace of the matrix, beta is negative of determinant. Then you can simply find those functions alpha and beta. Alpha is this particular function which can be converted into this form, kind of a whole squared form. And since we want to minimize this, you maximize sin 2 theta here, and so alpha turns out to be half. Similarly, beta is slightly more complicated because there are lots of sine and cosine terms multiplied. But if you keep on simplifying, that also can be simplified to a function only purely based on sin 2 theta. So of course, to minimize this, you need to maximize sin 2 theta, and just plug sin 2 theta as 1, and you get the value of beta as well, and you get the summation alpha star plus beta star as minus 29 upon 16. So all in all, I would say any ways you try to approach this problem, it does involve quite an amount of legwork. If you go to the first approach without using CH theorem, it just involves slightly more calculations. I would say 3 to 4 minutes of 3 to 4 more minutes of calculations will be involved, but eventually you will arrive at your answer. But even if you know CH theorem, you know how characteristic matrix equation looks like, and you do all the math and do all the comparisons, still some students might get caught up in this particular part. I don't think anyone will be caught up in this particular part for alpha. Some people might get caught up in this computation of beta, trying to bring beta into a function on a specific variable, in this case sin 2 theta. So that might be scary looking to some students, to be honest, due to which they might skip this problem. But otherwise, if someone knows CH theorem, it should be a pretty doable problem. I hope you got to learn something from this video. I hope what I tried to teach you in this video was very clear. If you have any suggestions, or if you want to see more such videos like this, feel free to let me know in the comment section. If you like this video, consider giving it a thumbs up, and feel free to subscribe to my channel if you like my content. We'll see you in the next one. Goodbye.